Okay, so thanks for the invitation to speak. I'm going to talk about an old story which was never really completely finished in all cases. As indicated in the statement, it's actually there's a preprint which is on the archive, which is a joint work with Yao, and we're still kind of refining it and getting the final version. It's a little bit technical. And so it has to do with the positive mass theorem, but really the generalized positive mass theorem. So that is in high dimensions. And so I'm not going to really focus very much on the precise asymptotics assumed, but basically the result that we're interested in is an n-dimensional manifold, Riemannian manifold, and the positive energy theorem in relativity really has to do with initial data. So it would also have a second fundamental form, and then the condition assumed would be the dominant energy condition. But there's a procedure which Yao and I developed way back in the early 80s to reduce the space-time positive energy theorem to the positive mass theorem that I'm going to describe, and actually that procedure is pretty robust. It's not so sensitive to the singularity issues that come up in this case. So the main case that we're interested in is this, where the energy condition from relativity corresponds to the scalar curvature being non-negative, and we assume that the manifold is asymptotically flat. Okay, and so under appropriate asymptotic assumptions, you can associate to such a so let's assume it's a complete manifold with, it could have more asymptotic ends, but let's just deal with one. Then the positive mass theorem says that the total mass, total ADM mass, is non-negative and zero only if mg is isometric to Rn with the Euclidean metric. And so that's the general statement, and I haven't precisely told you what asymptotically flat means because it won't actually be important in the talk. This theorem, of course, has a long history. So originally, Yao and I proved this theorem in an argument where we first did the three-dimensional case, but the argument generalizes to low dimensions. So we did it, so actually it works directly for n less than or equal to 7, but there's a separate argument to handle the 8-dimensional case. So this was an argument by using minimal hypersurfaces. So there's turns out there's a close connection between the geometry of minimal hypersurfaces and scalar curvature, and so it exploits that, and I'm going to describe that in more detail in this talk. The dimensional restriction there has to do with the fact that solutions of the plateau problem or volume minimizing hypersurfaces, oriented hypersurfaces, can be singular in high dimensions. So actually in dimension 8 or above. But in the 8-dimensional case, the singularities are isolated, and it's possible to get around them there. Okay, and so there's an argument in low dimensions using minimal hypersurfaces. There's also an argument for all n, but assuming the spin assumption, assuming spin. So this was an argument developed by Witten, also in the early 80s, and so it gives the result without the dimensional restriction, but it requires the topological, the spin assumption. And I should mention that in the three-dimensional case, there's also an argument which gives a little more general result, which uses the inverse mean curvature flow, uses a flow. And this was done by Schoen and Ilmanen, right, it's actually a separate. It's a different argument, but so far it doesn't have a generalization to higher dimensions. So it's not really relevant in my talk, but it gives a stronger result in the three-dimensional case. Okay, and so that leaves open some cases, namely the cases when n is at least 9 and m is not spin. And so there are two ways that you might try to approach the problem. I mean, you might try to take the spinor argument and try to somehow remove the spin assumption. And people have tried that, and so far it's not been successful. The other possibility, and the one I'm going to talk about, is to extend the minimal hypersurface argument to higher dimensions by sort of dealing with the singularities or working through the singularities. And so that's the approach we're going to take. So I'm going to describe a method for removing the dimensional restriction. So I want to take for all n, and without the spin assumption. So I'm going to consider the minimal hypersurface argument. I'll describe the argument. And so that's the main topic of the talk. And I decided to give a Blackboard talk just so that I could do it more informally. And so if you have any questions, I mean, there are a lot of technical issues involved, because whenever you deal with singular things, of course, life becomes more difficult. But I thought I would just try to give a somewhat technical overview of how the argument works and the basic strategy. So the first point I wanted to make is the reason I haven't defined what asymptotically flat means is there's a compactification procedure which simplifies some of the analysis. So initially the manifold, of course, is non-compact, and so that creates some difficulties with the analytical part. And actually, there's an old argument that goes back to really the beginnings of the positive mass theorem, which Yao and I did to simplify the asymptotics. Namely, we showed that if you had a counterexample to the positive mass theorem, then you could actually construct a counterexample which has very good asymptotics, in fact, which is conformally flat near infinity. And then more recently, maybe 10 years ago, there's an observation of Locamp, which I think was never published, which shows that using the conformally flat asymptotics, you can actually deform the metric, keeping the scalar curvature non-negative, to be Euclidean outside a compact set. Okay, so in other words, if you had a counterexample to the positive mass theorem in this form, you could produce a metric which is in fact identically Euclidean. And then you can take that metric, you can think of putting it in a big cube and extending periodically. And so when you do that, you produce a metric of non-negative scalar curvature, and then you can make it positive on a compact manifold. And that manifold is of the form a torus, the n-dimensional torus connected some with some other compact manifold. So the main theorem we're going to prove, which implies it implies the non-negative mass theorem, and from there you can get the general result. So the main theorem is going to be that if M0 is any compact n manifold, then manifold M, which is M0 connected some Tn, the n-dimensional torus, has no metric with positive scalar curvature, no Riemannian metric. Okay, and so again, statements like this were known in the same cases, namely in the low-dimensional case, there's a minimal hypersurface argument in general, and also Gromov and Lawson actually extended the Dirac operator arguments to include manifolds like that. So again, in exactly the same set of circumstances, this result is known. And so this result, as I said, implies the non-negative mass theorem, in the sense that a counterexample to an asymptotically flat manifold of this type with negative mass would produce a metric on a manifold of this form with positive scalar curvature. Okay, and so the advantage is this is a compact manifold, and it makes some of the analysis simpler. But I should emphasize we could do it without that. I mean, it's not. We could instead look at our minimal surfaces, which are asymptotically planar. It's just a little more work to do that. So it's just really for convenience, and really to focus on the main issues in the problem. Okay, and so let me describe the minimal hypersurface argument for doing this, and in a rather explicit form. And then I want to indicate how it can be modified to work with singularities. So that's the basic idea. And so the thing about manifolds like this is that that they have a degree 1 map to a torus. So I can look at a manifold M and I can map it to a torus. And then on the torus I can take the basic forms, one forms, dx1 up to dxn. We can just think of it as the Rn mod Zn, and then we have the basic n forms, and we can pull those back under the map pi. So we can look at forms omega I, which is pi star dxi, and when we do that, we produce we produce closed one forms. So these are closed, and with the property that the integral over m of omega 1 wedge up to omega n is 1. Okay. So these manifolds have a very special sort of cohomological structure. Namely, we can find a wedge product of closed one forms which is cohomologous to the volume form. Okay. And so what we then do is the following thing: we look at M. And then we look for a hypersurface in there. And so I'm going to index my hypersurfaces with their dimension. So I'm going to use the dimension as a subscript. Okay, and so actually in the argument there are lots of superscripts and subscripts. So this is just the notation that is taken in the paper. And so what we can do is we can produce a minimizer here. We can minimize volume under the condition that the integral, say, of the first n minus 1 of these guys is 1. So we can look at sigma hypersurfaces such that the integral is 1, and oriented hypersurfaces. We can assume our manifold's orientable to begin with. We can look at oriented hypersurfaces where we normalize the integral over the first n minus 1 to be 1. So we could get such a hypersurface by looking at the preimage of a t n minus 1 here. Okay, or looking at a level set of xn, the nth coordinate function. Okay, and so we can produce competitors for the problem, and this condition is well adapted to geometric measure theory. Namely, if we consider integral currents, then this is a condition. The fact that the integral is 1 is a condition that's closed under weak convergence, and so we can minimize the volume in that class. So we can produce sigma n minus 1, which has least volume subject to the homological constraint. Okay, and then the procedure is to choose on sigma n minus 1 a positive function. I'm going to call it un minus 1. And I'm going to, and actually the whole point is how to choose these positive functions. And so in the original argument, un minus 1 is just so without the singularities, you should think of un minus 1 as a lowest eigenfunction. So in the smooth case, that is in low dimensions, un minus 1 is a first eigenfunction of the second variation form. So this hypersurface is volume minimizing, so in particular it's stable. And so there's and it's two-sided, everything's orientable, so there's a quadratic form. It's only defined on sigma n minus 1, correct. That's right. So we take un minus 1, which is defined on sigma n minus 1, and we choose it to be a first eigenfunction of the second variation operator. And so I'm going to write that down. So if I take functions on sigma n minus 1, then I can think of them as giving variation. So I have sigma n minus 1, and I have a well-defined unit normal nu n minus 1. And so I can take phi times nu n minus 1 to be a normal vector field. I think of it as being a variation vector field. Variation vector field. So I think of moving sigma n minus 1, and then I compute the second derivative of volume. So I consider a variation, sigma n minus 1 of t. I compute its volume, and the fact that the second derivative, d second dt squared at t equals 0, this expression is Sn minus 1 phi phi. So it's a quadratic expression in the variation. The variation is defined by a function, so it's just a quadratic form defined on sigma n minus 1. And the condition, the stability condition, tells me that for every phi, this is non-negative. And so it's the second variation form which is related to the scalar curvature. And so let me just recall what it is or write it down. So Sn minus 1 phi phi is the integral over sigma n minus 1 of the gradient of phi squared. So this is the gradient along sigma n minus 1, and then a zero order term. So it's minus 1/2 the scalar curvature of m. Let me call that Rn, and then minus Rn minus 1, which is the scalar curvature of sigma n minus 1. So it's the difference of the scalar curvatures. And then there's another good positive term, which is the square of the second fundamental form. So let me call it An minus 1 squared, and then times phi squared. That's this whole thing with respect to the volume measure. Okay, and so the condition that this form be positive definite or non-negative definite implies that there's a lowest eigenfunction, which I'm calling un minus 1, which doesn't change sign. So I can normalize it to be positive, and that's what the un minus 1 is in the classical argument. Okay, and so then the way the argument works is we use un minus 1 as a weight function. So you can think of it as a conformal deformation, but it's a little nicer because I want to keep the original metrics. So it's important in the singularity argument that everything be a submanifold of a given smooth manifold. And so we want to keep track of the original geometry, the geometry induced from M. Okay, and so what I do then is I produce in sigma n minus 1 a sigma n minus 2, another hypersurface which minimizes a weighted volume. And so sigma n minus 2, maybe I can squeeze it in up here. So this minimizes a volume which I'll call V. And so I'm going to call this rho n minus 1. It's the n minus 1 weight. So it minimizes V rho n minus 1. And so that's the integral over a sigma. Now it's n minus 2 dimensional of the weight function rho n minus 1 d mu n minus 2. Okay, and so when I do that, I can repeat the procedure. So I can, for this weighted volume, I can compute its second variation. Actually, with a suitable geometric interpretation, it's really the same, essentially the same formula. And then I can produce on sigma n minus 2 a positive eigenfunction, which I'll call un minus 2, n minus 2. Positive. So again, it's a lowest eigenfunction of the corresponding stability operator now for the weighted n minus 1 volume. Okay, and then I modify the weight function by multiplying these two guys. So I now take, I'm running out of space here. Let me rewrite it here. So I have mn contained in, I have the hypersurface sigma n minus 1, un minus 1, which I'm also going to call rho n minus 1, and then I'll get sigma n minus 2, which minimizes the weighted volume, weighted by rho n minus 1, and then I get a un minus 2 here, which is again positive, and I define rho n minus 2 to be the product. And then I repeat the procedure. So the argument then gets repeated, and I go down to some dimension, say sigma k. So k is something less than n. And in general, the inductive procedure is that sigma j minimizes the weighted volume v rho j plus 1. And subject to the same sort of homological constraint, namely the integral of omega 1 wedge up to omega j is 1 on sigma j. So I impose that condition. I look for submanifolds that satisfy that and are contained in the original in sigma j plus 1. And then I minimize it, and that's how I produce sigma j from sigma j plus 1. Okay, and so the argument goes down.
Taking away the problem, you could have just geometrically interpreted that as saying you're taking the conformal rescaling.
I could have, but I don't. So in the singular case, it's important not to throw away the metric. So I have to use in the singular case the ambient geometry as well. So yeah, I mean, there's an easier way to say this whole thing if you don't have to worry about singularities. You can view it as conformal change of metric. You can also there's a different geometric way to view it, which is actually a little sharper, and I'll describe that in a minute. And it again goes back to the beginnings of the theory. So actually, a little nicer way to, well, let me come to that in a minute, but let me just finish the discussion. Okay, and so this is the procedure. And so the object of study here, we've given a name which is called a minimal K slicing. Okay, and so it just means this procedure, namely you start with an n-dimensional manifold, you produce a minimizing hypersurface volume minimizing, you produce a weight function. Well, we did it using an eigenfunction of Sn minus 1. We're going to modify that a little bit in a minute, but and then you repeat the procedure and you go down to some dimension. So say we go down to dimension k. Now the basic geometric facts. So there are sort of two sides to the story here. There's the geometric side, which is that if we make these choices, that is, if we choose our weight functions to be lowest eigenfunctions of the second variation operators, the geometric side is that if I produce a smooth, if I start with positive scalar curvature, so I assume that Rm is non-negative, say strictly positive, then sigma k, R sub n, thank you. Denoting things by, yeah, so if we start with positive scalar curvature, then sigma k is Yamabe positive. In other words, sigma k also has a metric of positive scalar curvature, and you can get it by conformal deformation. Okay? So it means that the conformal class of sigma k has a metric, contains a metric of positive scalar curvature. So that's sort of the geometric side of the story. And in particular, it gives the proof of the theorem because we can go, so in the case we're considering the connected sum of a torus with a manifold, we can go down to k equals 2 or even 1 if we wanted to. But if we take k equals 2, then it implies that sigma 2 is a union of spheres. Of two spheres. But on the other hand, we produced sigma 2, okay, but that's a contradiction because remember the integral over sigma 2 of omega 1 wedge omega 2 was 1, right? And that's a contradiction. Because that means that the one forms omega 1 and omega 2 are not exact on sigma 2. So in particular, sigma 2 can't be simply connected, and so that's the basic argument. So you can do this procedure and starting at dimension n, you can then produce this minimal 2 slicing, and you conclude that the two-dimensional slices, if you started with positive scalar curvature, have to be spheres. And so that's sort of the geometric side of the argument. Now, the question is then, what happens with singularity? So why the dimensional limitation? Well, the problem is, so suppose I took n to be, in fact, greater than or equal to 8, and I try to do this argument. Then I immediately run into some trouble because if I take n greater than or equal to 8, then sigma n minus 1 could have a singular set. So sigma n minus 1 then consists of the regular part, and we call it Rn minus 1, union a singular part, Sn minus 1. And we know, it is known that Sn minus 1 is a very thin set. It's a set of high codimension in sigma n minus 1 in the Hausdorff sense. We don't know the structure very precisely, but the Hausdorff dimension, it's a closed set, and the Hausdorff dimension is at most n minus 8. So that comes from the the minimal hypersurface regularity theory. So this goes back to the late 60s and early 70s. In fact, we're at the Simons Center, so Simons' result plays a very big role in this result about study of minimal cones. Minimizing cones plays a big role in this argument. So this is the minimal hypersurface regularity theory. So there's this kind of weird phenomenon that in low dimensions these things are completely regular, but in high dimensions they can have very thin singular sets. Okay? And so then if you think about this, so Sn minus 1 is some very high codimension set. On the other hand, when you produce the next slice, let's suppose we could produce the eigenfunction and produce the next slice, then it would be unrealistic to expect the next slice to miss that singular set because it's a hypersurface. And so as long as the dimension of this is bigger than 1, then you would, in principle, expect it to encounter the singular set. And so what's likely to happen, or what you would expect to happen, is that when you start in very high dimensions, the slices, the first slice may have some singularities. The next slices may encounter the previous singularities, right? And so, on the other hand, the eventual argument, as we described, goes down, eventually slices down to 2 dimensions. And so, if you could somehow produce the slicing and the eigenfunctions in the slicing, then it's not unreasonable to expect that the 2-dimensional slice could be everywhere regular. So the hope is that we can somehow produce the slicing in the singular setting. And although the slices may be singular on down to some dimension, they may have some singularities. We want to control the singularities and show that the 2-dimensional slice is actually regular. So the idea is to control singularities of the kth slice, sigma k, and show that sigma 2 is smooth. In other words, sigma 2 doesn't encounter any of the previous singularities. It just lies in a regular part of the top dimensional slice. So sigma 2 and all previous slices are regular in a neighborhood of sigma 2. So that's the hope. See, the argument is sort of local in the sense that the second variation argument only sees a small neighborhood of sigma, right? And so if there are singularities far away, that doesn't really make any difference in the argument. So the idea is that in this situation where we eventually cut down to very low dimensions, in particular dimension 2, we eventually get a regular slice. Once we have the 2-dimensional regular slice, then the arguments are all local. So that's the strategy. So we're not claiming that the slices are regular, if they miss the singularities in general in high dimensions at all, but what we want to show is that we can control the singularities for each slice. That's the idea. So actually, the philosophy of the argument is quite consistent with the ideas of geometric measure theory. So in geometric measure theory, you look at singular objects in general, and the singularities typically are just part of the problem. And so that's sort of the idea here. Of course, when they're there, they're harder to deal with. It makes the problem harder. But that's the basic idea. And so, as it stands, so the question is, how do we get in order to control the slices, we need to understand. Well, we need to prove that so first of all, we need to construct the eigenfunctions, which they may blow up on the singular set, but they don't blow up too badly. We need to be able to control the eigenfunctions we construct. And to do that, we have to exploit the situation. So I talked about the geometric side. There's also an analytic side to this, which maybe is slightly hidden. And that is in the geometric argument, So when the slice becomes singular, the second fundamental form, of course, will blow up. And so if we were able somehow to control integrals involving the second fundamental form, that would give us some sort of weak control near the singularities. And so in the geometric argument, you throw this term away. And there's another. I haven't given you the whole argument. There's another term, positive term later, that also gets thrown away. That's useful analytically. So the analytic side, we need to exploit these extra terms. Otherwise, you see, the only thing we have going for us is that the second variation is non-negative, right? So we only know it's non-negative. We can't use it to bound anything, right? Because it could be zero in some direction. So what we need is we need to modify the second variation form to make it more coercive, so we can use the lower bound to give us estimates to control the eigenfunctions and then hence the ultimate slicing across the singularities. Okay, and so that's the first idea. So the idea is we're going to modify this form. So we're going to take, and maybe I won't say exactly how it works because it's a little bit technical, but let me just say what we can control in terms of the. So the analytic side we need to control the eigenfunctions and the later slices across the singular sets of the previous slices, right? And so in order to do that, we need bounds on things. We need the eigenfunctions to be bounded in some weak sense, some integral sense at least, across the singularities. And so the way it's done is the following the following idea. So what we're going to do is we're going to consider what happens if we modified the second variation form. So suppose we took Qn minus 1, the new quadratic form, which is Sn minus 1, a phi, and then plus something. So we put in, in general, Qj to be Sj plus the integral over sigma j of some positive function, pj times phi squared. d mu j, and actually this will be a weighted volume, rho j plus 1
In the singular case,
d mu j.
it's not so clear that all the variations you want to consider are actually given by. I mean, there's not really a
Right. So all of the arguments involving the second variation work only on the regular set. So we never consider variations. We never attempt to consider normal variations that move the singular set. So they're always restricted just to the regular set. So this Yamabe positive argument only works if sigma k is everywhere regular. We don't make any claim in the singular setting.
So phi is always supported in the singular?
Phi will always be supported in the regular set. Yeah, right. Yeah. Okay. And so I want to consider what happens when we add a positive term here. So pj is going to be some good positive term. And suppose instead of considering the Sj, I considered this Qj. So then, how does it affect the argument? So I want to allow Pj to be terms that help us near the singularities, so they blow up at the singularities, right? And so how does it affect the geometric argument? So the basic, we can describe it in the following way. So let's just look at j equals n minus 1 for a minute, the first one I wrote. so if we consider the un minus 1, which was the let's say we take un minus 1, which is the lowest eigenvalue of qn minus 1, then the important thing, and I didn't say this, but the geometric interpretation that I'm interested in for the second variation form, the original un minus 1, is that I want to consider, so these weighted volumes actually are best interpreted not as conformal metrics, because I want to keep the original Hausdorff, the original Hausdorff measure on coming from the smooth manifold. But the best way to interpret it is that if we take sigma n minus 1 cross S1, where we take the metric gn minus 1, the induced metric from M, plus un minus 1 squared, dt squared. Let me call it dtn minus 1 squared. All right, so we cross with S1. Then the condition that un minus 1 be a lowest eigenvalue of the second variation operator implies that if I compute the scalar curvature of this metric, so in the paper this is called the g hat metric. If I compute r hat n minus 1 using the fact, so if I just compute the scalar curvature of a metric like that, you can check that you get minus 2 times Laplacian n minus 1 un minus 1 over un minus 1, and then plus the original scalar curvature rn minus 1. Okay, and then if you plug in the condition, the eigenvalue condition, so the condition that un minus 1 is a lowest eigenfunction of this operator, you can see that the rn minus 1 is going to cancel out, right? So that's the term we don't know the sign of. And so what we're going to get when we plug it in is that this is equal to the original scalar curvature, Rn, and then plus a positive term. There's a positive term that involves this an minus 1 squared. So, and there's a norm of an minus 1 squared, which I think occurs with a factor of 1. So if you just plug in the, and then there's a lambda 1, which is positive.
So this is the lowest eigenvalue in what function?
This is on, so this is in the smooth case. So in the smooth case, the interpretation I want to give for these weights is not the conformal one, but this one. So notice if you took a hypersurface in here and you crossed it with S1, so you can think of this as being S1 invariant metrics. If you took an S1 invariant hypersurface, its volume is precisely the weighted volume. Okay? And so really what we're doing at each stage is we're minimizing the ordinary volume in a warp product where we add a factor of S1 for each time we do the procedure. And so you can interpret the whole thing. And so you never actually have to recompute the second variation. It's always the same form, but in this warp product. Okay? And so we're doing that. And the nice thing about the procedure is the lower bound on scalar curvature persists, right? So if Rn has a lower bound, then R hat has the same lower bound. So you don't lose anything in the argument. Whereas if you do the conformal argument, you'll lose. You won't be able to show that. So these metrics all have the same curvature bound. But the point is that there's an extra term left here. Okay, now if we modified the procedure and replaced Sj by this quantity, then what we get is a minus Pj here, the positive term. So in other words, the effect of making the form more coercive is that you're in danger of messing up the geometric argument. Okay? And so you can afford to make it, you can afford to add certain positive terms, but you can't afford to add too much or you'll mess up the geometric argument. Okay? And so on the other hand, you see that we could at least take Pj to include part of that second fundamental form term. Okay? And so in fact, there's a little more complicated procedure. If you study the slicing in general, you actually get better terms, and in fact, you can choose. So Pj can't be too big in order to keep the geometric argument, but it turns out that Pj So this is a little bit surprising, but Pj can be chosen to be bigger than or equal to some positive constant, epsilon n, times the norm of aj squared, the full second fundamental form. So sigma j, of course, is contained in M. So it's a high codimension submanifold. But on the other hand, it has a very special structure in that the slicing gives you, in the normal bundle to sigma j, it gives you a trivialization. It gives you nu j, which is contained in sigma j plus 1, the normal in sigma j plus 1. And then you have nu j plus 1, which is the normal of sigma j plus 1 in sigma j plus 2, and then on up. So in other words, these slicings come with a trivialization of the normal bundle. And at each stage, you get part of the second fundamental form in the process. So in other words, you can make the argument in such a way that you can add a positive term which is bigger than the full second fundamental form. This is the vector valued second fundamental form in M, the original M. So it's saying something about singularities, how it blows up. It's saying something about it's the extrinsic curvature of sigma j in the smooth ambient manifold. So that's the first point. And then you can also, and again, this is a little harder to explain. You have to get into the guts of the argument. But you can also add here expression. So this is a weighted volume. You can also add, you can also remember the derivatives of the...
In the direction of which normal? It's the one that's from the first hypersurface or from the last one?
This is the whole second fundamental form. So it's the sum of squares of all of them. This is the second. So this is the second fundamental form in M. So so at each stage of the slicing, you get the second fundamental form in the corresponding normal direction. Then at the kth slice, you get the full. You can control the full second fundamental form. That's the claim. And so it's really saying something. Otherwise you'd just be controlling the second fundamental form in some singular manifold, and you don't know what that means. But you have to remember that everything is contained in a smooth ambient manifold. So if I had a bound on that, then that would give me the regularity of the sigma j. And you can also control. So remember, these are weighted, but you can control the log of up squared. Some p goes from j plus 1 up to n minus 1 as well. And so it turns out you have to, it's a computational argument to check, but you can choose pj to be big enough so that it dominates positive constant times that term without messing up the geometric argument. Okay? So in other words, the claim is I can replace the second variation forms by forms which are much more coercive and which give me control on the eigenfunctions near the singular set without messing up the geometric argument. Okay, so that's the key step for the first.
Are positive away from the singular set. How do they behave towards the singular?
Right. So what they are is they are in some weighted Sobolev space which has a weight thing that looks like that. So the control is only integral control. So they're in an L2 space. They're L2 with respect to the weighted volume, and they're also in a weighted Sobolev space. So the integral of gradient squared plus this pj, or plus this term, times u squared is bounded, right? Because we get them by minimizing this form. So that gives us control. That gives us enough control on the u's to make the argument. That's the claim. Okay, good questions. Any more questions? Nobody ever really follows this argument. It's a little bit technical, but actually, I gave like 8 or 9 lectures on it at ETH last year. So, and there's a set of notes which I'm in the process of polishing up that has more details plus some other related material. Okay, so yeah. Okay, so then what's the basic idea? Okay, so let's see. Yeah, Okay, so so how does the argument go then? Okay, so what we do, so the procedure is as follows. So we look at, so just as in the smooth case, we take sigma n minus 1 contained in M or n manifold, and then we construct un minus 1, which is positive, which is now a lowest eigenfunction of this form qn minus 1 is associated to qn minus 1, and it lies in a weighted Sobolev space. So it's not, of course, not, they're not bounded, and we don't have pointwise control near the singular sets, but the un minus 1 is in a specific weighted Sobolev space. So this lies in qn minus 1. And okay, so one of the theorems in the paper is to show that the form qn minus 1 can be diagonalized, or qj can be diagonalized with respect to the L2, the weighted L2 norm. And that's based on the fact that you have these positive, you have control on these terms. So basically all of the theorems in the paper, the analytic results are all sort of non-concentration theorems. And so the idea is we're working on this manifold, which is mostly smooth, but there's a thin singular set. And so the whole issue really, because on the regular set you have good control. So the whole issue really is to control things across the singular set and to show that, you know, L2 norms or W12 norms or whatever don't blow up on the singular set. So it's that kind of idea. The whole issue is to control things across the singular set. And that's precisely what these extra terms allow you to do, along with various other arguments. And so you do this whole thing in the singular setting, sigma n minus 2, un minus 2, and then so we look at a k-slicing where we've now, so once we construct the eigenfunction in the suitable space, we then need to construct the next hypersurface. And so how do we do that? Well, the key thing is that we can find a competitor for the problem. And so a competitor would have finite weighted volume. And so the fact that you can find such a thing follows from the growth assumption of the weight function near the singular set. Okay? It's based on so a lot of the arguments, the boundedness arguments, in other words, getting bounds on things, are based on comparisons. So just like for the plateau problem, if you want to estimate the volume inside a ball, you can do it by comparing to half of the ball, right? So this is less than, say, half. So you can argue if you have a proper oriented minimal hypersurface in a ball, you can estimate its volume. Same kinds of ideas work here. So you can estimate locally the volumes of these things by comparison arguments, by slicing. In other words, because we're in a smooth ambient manifold, we can and we have integral bounds on, you know, the weights on one slice. We can argue that for almost every sphere we cut with a smooth function, we'll get corresponding bounds. And so we can use that to produce competitors. And then the minimization, the GMT part, is really just works on the regular set. Again, so you minimize so that you minimize among relative cycles, in other words, and so you can produce the slicing and the eigenfunctions in this way, and then the key argument is, so if we take sigma k, we can then write it again as a regular part union a singular part, sk, for any of the case. You have to do this analysis in the correct spaces, and then you produce these sigma k's. And the definition here of regular, so a point P in RK, P is in RK if there exists an epsilon positive, so that all of are smooth. So in other words, near a regular point, the sigma k is smooth, and all of the previous ones are smooth, just for j greater than or equal to k. Right? So being regular by definition means that I have a smooth point of sigma k, and all of the previous slices are smooth. So that's the regular set. So by definition, it's an open set, and so the singular set's the complement. So it's a closed set. It's a closed subset of sigma k, and the whole point is to control the size of that set. Okay, and so And so let me just say, let me just give the basic idea here, and it's, again, so the key issue, I mean, the reason this doesn't just follow from minimal hypersurface regularity theory is that SK consists of two parts. So SK consists of the part that was singular in the previous slice, SK plus 1, union the part that was regular in the previous slice. Right, so there are some points in SK, singular points, which were singular in the earlier slice, the bigger slice, bigger dimensional slice. There are some points that were regular. Well, this set is no problem, because if we were regular in the previous slice, then we would just be looking at a standard volume minimization problem, and this would have the Hausdorff dimension of this part's very small. The dimension would be less than or equal to k minus 7. So that's a good part. The difficult part to handle is the part that was singular previously. In other words, the problem is that the hypersurfaces will contact the earlier singular sets. Okay, and so it's really controlling this part that's the whole issue. Okay, and so let me just sort of describe how that's done. So the key to doing that is, The hint is provided by the ordinary minimal hypersurface regularity theory. So I mentioned the result for just minimal hypersurfaces. Well, that's actually a special case of this, right? If I did an n-1 slicing, then I'd just be looking at a volume minimizing hypersurface. And the thing about volume minimizing hypersurface is that you can study the singular set by ultimately using the regularity theory. You can reduce it to tangent cones, homogeneous solutions. And so that's the idea here too. So for a minimal hypersurface at any singular point, there's always a non-trivial tangent cone, a non-flat, non-planar tangent cone. And so because of the way we construct these eigenfunctions, they're in these weighted Sobolev spaces, and then the sigmas, we can do the same thing here. So it turns out, so this is sort of the main, one of the key steps, is it turns out that at a singular point, if I take a point which is singular in SK, then at that point, by successive rescaling, I can produce a homogeneous minimal K slicing. There exists a non-trivial and so what that means is that I have cones. So CK is a cone contained in CK plus 1, contained in Cn minus 1, contained in Rn. So I'm blowing up, so the manifold becomes, the ambient manifold becomes flat. And then I have the corresponding weight functions, Un minus 1, Uk plus 1, Uk, and everything is homogeneous. So the key thing is to show that by rescaling, you can produce a non-trivial homogeneous K slicing. So that means these Cs are cones. Each Cj is a cone. And each Uj homogeneous of some degree, of some finite degree. I don't know whether the degree is positive or negative in general. So it's possible that the Uj could go to 0 near the vertex, or it could conceivably blow up at some rate. But it's controlled. It's in some L2 space, so the rate of blow up is controlled. So that's the key thing. And to do that, so in the minimal hypersurface case, that's done using compactness theorems. That is, you have to be able to take limits of these blow-ups and monotonicity. So it's monotonicity. So here again, there are two monotonicity results. There's the monotonicity, a modified monotonicity of volume, and there's also a monotonicity which is associated to the UJs becoming homogeneous. And that's this great idea of Almgren going back to the maybe late 70s, which involves the frequency function. So it turns out because these U's lie in these weighted Sobolev spaces, you can find a monotone frequency function which causes the blow-ups of the U's, assuming that the background space is already a cone, it tells you that you can produce a homogeneous blow-up for those. I don't have time to write that down, but it's a very robust kind of monotonicity formula which works in this singular setting. So it really only uses the fact that the U's minimize this quadratic form, and it does simple variations to produce that. So there are two monotonicity formulas that go into it. One of them produces. So the way this works is if you take a point which is singular. Well, if this is regular, then you go down to the first singular cone that you get, and at that point you blow up and you get a non-trivial minimal cone, and now you carry along the entire structure to that minimal cone. So now you have a minimal slicing which starts with a minimal cone, and then because of the homogeneity of the cone, you can use the frequency function to blow up again and make the eigenfunction homogeneous. Once it's homogeneous, you can then prove a modified volume monotonicity and show that the next one is homogeneous. You can go down. So all of the arguments here go down. They're from the top down, right? So like trickle-down economics, right? So you just pointed to a big gap. Right. Yeah. So it uses the fact that we know the theory, in the highest dimensional case is just the minimal hypersurface theory, and then we use that to get the next one and then induct down. So we assume the result at dimension k plus 1, and then to get the dimension k result. So a key thing is that at each singular point you can produce a homogeneous k slicing, and then the way the argument goes, the geometric argument that I didn't describe in much detail, but let me just say it. Actually implies something about these homogeneous slicing. It implies there exists no non-trivial homogeneous minimal 2 slicing. Two slicing with an isolated singularity at the origin for the sigma 2, right? And so that's a consequence of the geometric argument. It uses the second variation again only for variations supported in the regular part, and the two-dimensional case is special because a two-dimensional cone is flat, and so there's the geometric argument that I didn't describe in full detail actually also has the analytic consequence that we can rule out homogeneous minimal 2 slicings. Now, the effect of that, based on sort of geometric measure theory ideas, is that we can prove that the singular set of sigma k can never become larger than k minus 3 dimensional. And so that's the main regularity theorem. So the main regularity theorem is and actually this doesn't have anything to do with positive scalar curvature. Would work in any smooth manifold or even locally. So the main regularity theorem is that the dimension, Hausdorff dimension of Sk is at most k minus 3. Okay, and the idea of the proof here is it's a little bit similar to the again, it uses some ideas from geometric measure theory involving dimension reduction and also sort of density arguments, measure arguments. It's done by induction. So by downward induction, by trickle down, right? So you assume that the singularities are codimension 3 at, say, slice k plus 1, so they're at most k minus 2 dimensional, and then you produce sigma k, the k-dimensional slice, and then if you assume that its singular set had Hausdorff dimension bigger than k minus 3, then you could produce, by choosing a good point, a sort of point of density of the singularities and blowing up at that point and successively blowing up, you could produce a cone like this, a homogeneous minimal two-slicing. And then the non-existence of the two slicings with an isolated singularity give you this regularity result. In the same way that Simon's proved that there are no minimizing cones in dimension less than 7. And so that result, together with some regularity theory in GMT, implies the singular set is at most Hausdorff codimension 7. So it's the same idea. I mean, so we don't know how to rule out minimizing homogeneous slicings in dimension bigger than 2. If we could, it would give us a lower dimensional singular set. And so the whole idea is the way the singularities are controlled, again, is by showing, well, there are various analytic theorems that go into it, but by showing that at each singular point you have a non-trivial homogeneous slicing, and then the fact that those don't exist in 2 dimensions gives you, through these sort of GMT machinery, the result that the Hausdorff dimension is at most k minus 3. And so in particular, when k is 2, if we do a 2 slicing, it's everywhere regular, and so the argument works. So that's the idea. Okay, so I think I'm over my hour. So
Rick, thank you very much. Any questions?
Yeah.
Do you expect that this regularity can be improved eventually?
Well, actually, there is a kind of obvious minimal 3 slicing that I don't know if I don't know if it's minimizing or not. But so the Simon's cone is S3 cross S3, the cone over that in R8. So you can construct. So if you look at the eigenfunctions there, they'll just be radial functions, and so you can construct within that using symmetry. If you weaken the symmetry group, you can construct a slicing which is stationary and ends at the Clifford torus, say. So you can like S3 cross S3, S3 cross S2, S2 cross S2 on down. And so there is a natural one. Whether it's whether it's checkable, I think, whether it's stable or not. In fact, I asked a student to look at it, but he didn't ever do anything on it. But but even if you know it's stable, of course, you don't know if it's minimizing or not. So one thing I should say is that the details of this depend to some extent on some arbitrary choices. So these quadratic forms, the constant that appears, the term you add to the quadratic form does could conceivably affect the structure of the singularities. I mean, whether it would, I don't know. But that's another point. I mean, it's not a completely canonical procedure. It's there is some flexibility there. So the answer is I don't know. I think it would be, I mean, there's no simple argument to get the next dimension, to rule out 3-dimensional cones that I can see.
Someone else have a question?
Yeah. Oh, that was the same question. Okay. Yeah.
You said that this is the regularity theory does not really involve the scalar curvature, but the
Yeah.
UJ does, right?
Yeah, so actually, after you blow up, the scalar curvature goes away. It goes to 0. So yeah, so in a certain sense, maybe what I'm saying isn't quite right. It's both the geometry and the analytic part that does. So it's the fact that I mean, it's the way that we modified the form not too drastically, so that we could still get the correct eigenvalue conditions that implies this second part here.
Non-negative scalar curvature.
Well, the only, yeah, just in the smooth case. Well, I mean, there's a possible borderline case. I mean, it could be Yamabe 0. Actually, Greg has looked a lot at that kind of thing, and so in the argument we're looking at, for these manifolds, if you have a metric of non-negative scalar curvature, you can deform it to be positive, anyway, and so that gets around that problem. But yeah, technically there is a kind of borderline case where it's like Yamabe 0. So in the 3-dimensional case, instead of a sphere, you could have a torus. With Yamabe 0, then it would have some special structure. But we don't really have to deal with it here. We can.
It'd be very special in Yamabe 0. Actually,
it would be, yeah. So a neighborhood of it would look flat. I think the Ricci curvature in the normal direction is 0, and the metric is flat. Yeah. So it has some special structure. Yeah.
Or
Yeah, and so actually, Greg, I think if you assume it's minimizing for a problem, then I think you can rule it out, right?
When you expand these out to make the column just like it's like it's scaling of negative at the formula. Well, it's already.
Yeah, so once you, you can start in any smooth manifold. When you blow up, it'll be in Euclidean space. So, yeah.
Are there any other questions?
So I have a question on for the general initial data set. Do you know if
Yeah.
there's any abstraction to deform the initial data set with dominant energy condition to?
Well, it involves the Jung equation. So the solution of the Jung equation, of course, is smooth. It's a graph. So if the solution exists, then it just works. But in general, the solution can blow up on a MOTS, right? And so either a forward or a future or a past MOTS. And so the MOTS, in principle, could have the thin singular set like this. On the other hand, I don't think it really matters because ultimately the argument involves sort of, blowing that up anyway. So it kind of becomes a barrier. So I believe that argument should work in the singular case also. But I haven't really written it down. But I don't think the singularities are essential in that argument.
Without using John's graph, do you know if there are example of initial data set?
Oh, I see. Using the positive mass, this other approach. Then I guess you'd have. So maybe you could do it that way, right? And you could start with. That's possible. And then maybe it would just, so at the first stage it would be in this non-negative scalar curvature type setting. Yeah, I don't know. I've been busy trying to get this case, and I haven't really looked at that yet.
What is anything known by now for this problem with asymptotically hyperbolic boundary conditions?
You mean positive mass theorem?
High-dimensional case.
High dimensional. The singularity, the regularity theory is local. So if there's an approach using mean curvature, like in that case maybe CMC surfaces, then I believe that this should allow you to carry it through to higher dimensions, I would think. Whether it's minimal or CMC doesn't make very much difference in the theory. So I believe it should. If there's an argument in the smooth case, it should extend, I would think. But I'm speculating, of course.
Other questions?